In this lecture, we're going to go ahead and design a beam bearing plate. Sometimes when you have a beam resting on a concrete, you may require a bearing plate, and really it's a good idea to put a bearing plate there because the reaction force from the beam, or the weight of the beam with all the load on it, and you like to see it to distribute evenly over the concrete or masonry wall. And so that's why it's good to have put a bearing plate here. So let's take a look at this example. As we go through the example, we explain the code because there's a new code to do this thing, and we're going to use the 16th edition. So we have this W18 by 50, and the reaction, the weight on top of this beam, the reaction is dead load is a 15 kips and a life load is a 45 kips, and is supported by a 10-inch concrete wall. So the available bearing length for us is about 10 inches. And if you look at the cross-section view of the beam, this is W18, and this be proposed bearing plate, and there is your dimension from these are your basically KDDS, and your N and your total B. So we're going to work on that. And one of the things we're going to do is we're going for beam and the plate, we're going to use FY50 KSI, which has a FU65 KSI, and the concrete it's a 3,000 pound concrete. It's a 3 KSI stress. Going to table 1 of AISC, which you see on the board, I have written down the D is equal 18 inch, TW is 0.35, your flange width is a 7.5, and a flange thickness is 0.75. KDES is 0.97, and K1 is 13/60. One of the first things we're going to do, we're going to use AISCE 722 to find out our load, both in load resistant factor design and allowable stress design. So that is 1.2 times dead load of 15 kips plus 1.6 times life load of 45. That's equal 90 kips, and on this side it will be, so I'm going to just write 90, that become RU. So just let me write here, say RU is equal 90 kips, and RA is equal basically 15 plus 45, and that's equal 60. Board, take a look at it. Number one, I want to check the limit state of web local yielding, and that comes from a table 9.4 equation 960 A and B of the AISC 16th edition. Then we can check the local web local crippling, and that's equation 963 A and B, again table 9.4. Then after that we can check the bearing strength of the concrete. Then we can check the beam flange limit state and find out if the thickness of the flange is good enough, or is it gonna not gonna be making it. So let's go ahead and get to work. First thing we're gonna do, we're gonna go ahead from table 9.4 equation 960 A and B. We're gonna go in there. As you can see on the screen, I get phi time R1 43.1 kip and phi time R2 17.8 kip per inch, and same thing for R1 divided by omega and R2 divided by omega. And those the number for ASD and load resistant factor, load resistant factor design and ASD. So from the code again, LB minimum is equal these equation, RU minus phi time R1 divided by phi time R2 should be bigger than KDES, and same as for allowable stress design in the RA and omega involved. And these are given from the table, so I'm going to go ahead and say LB minimum is equal, RU was 90 minus phi time R1 43.1 divided by phi time R2 17.8. That should be bigger than equal than KDES 9.972, which I got 2.63, which is bigger than equal than 0.972. We have 10-inch available, so 2.63 is less than 10-inch available, so we okay right here. We do the same thing over here. LB minimum for allowable stress design is, that's a 60 minus 28.8 divided by 11.8, and that's almost same thing, 2.64. 2.64, which is bigger than, I mean, less than KDS 0.972, and again, it's less than 10-inch available. So we did our first check, which was web local yielding. Now we're going to go ahead and check for web local crippling. Let me erase this board and we come back to you. So we're going to do web local crippling based on AISC 9.4. But the first thing we do, as it shows in the manual, we're going to check LB over divide by D. The available length is 10 inches, and then our D is 18 inches, and that came out to 0.556 inch. And based on the code, since that's bigger than 0.2, then we are allowed to use these equations right there. So let's go ahead and proceed. From the table 9.4, we can find R5 and R6, which they are for crippling. Then the bearing length minimum, it comes out by these two equations, just like the last one. So we're going to say, okay, LB minimum is going to be RU, which was 90, minus 52, divide that by 6.3, and that should be bigger than 0.972. In this case, comes out to be 603, which is bigger than 0.972, and also 6.303 is less than 10 inches, so we okay there. Same thing over here. It's going to be LB minimum is equal 60 minus 34.7 divided by 4.2, and that should be bigger than KDS, which comes out to be 6.02, which is bigger than 0.972, and also 602 is less than available 10 inch, so we are okay there too. Now, when we said LB over D, we use 10 inch over 18. What about the actual? It's going to be 6. So if we're going to say double check it to verify, let's check it. We're going to have LB over D, and our LB is 603, and divide that by D, 18 inches, comes out 0.335, which still is bigger than 0.2, so we okay here, and that's going to be the same thing because it's the same number anyway. 602 divided by 18, and probably same number, 0.334. Bigger than 0.2, we still okay there too. Okay, so that was number 2. We checked for web local buckling, web local crippling. Let's now check, see if the concrete is strong enough for this load. I'm going to erase this, we come back to it. Okay, the first thing we're going to check is bearing strength of the concrete. We're going to use the specification of AISC equation J81. Take a look at that page, or go into a manual, take a look at it. We have A1 and A2. Our A1 basically is the area of the steel underneath the, or on top of the concrete, the full bearing length of the steel. And then we have the A2, which is the maximum area of the portion of supporting surface. In this case, our A1 is bigger than A2. So A1 is equal BF times LB is right this whole area right there underneath it. And that's going to be, the BF is 7.5 inches. And the total concrete is a 10 inch available. That's a 75 inch square. And then I'm just going to go ahead, it's no AISC, or just going to write an equation here. The J1 is PP is equal 0.85 times F prime C. Let's figure that out quickly, and that is PP is equal 0.85 times 3 KSI times 75. Again, this is not any of those, and that's equal 191 kip. Now I can go allowable stress design and low resistance factor design. I can basically do this, right? Say low resistance factor design and AISC. Pins 0.65 times 191, and that's equal 124 kips. And our 124 kips is bigger than our original 90, so that's okay. And over here we have PP divided by omega, which is 191 divided by 2.31. That's 82.7, which is bigger than 60, so the concrete checks out. That was easy. So the next thing we're going to check is we did the local buckling of the web, local crippling of the web, the bearing strength of the concrete. So just look at the flange, see the flange is strong enough for have all that load on it. Let me erase this again. Now we're going to check the flange, see the flange's the thickness is strong enough, or is it going to kind of curl up or bend. And we're going to check the thickness, if the thickness is strong enough. And if we go into the AISC equation 14.1 to take a look at your manual, take a look at that. We're going to calculate, and N is right here basically, and it's going to take out the K. These two K become KDES, K design. So we're going to say, okay, BF divided by 2 minus KDES. And that was a 7.5. divided by 2 minus 0.972, which is equal 2.78 inch. Take a look at the equations I got on the board. We're going to use those equations from the manual. First, we're going to calculate, we're going to see the bearing pressure is given by those two equations, both in allowable stress design and low resistance factor design. Then the required flexible strength is given for the flange. We all know that. It's given by mu is equal to FAP, n squared divided by 2 is just a moment. And then you have our phi is a 0.9 and omega is 1.67 for bending. And then you can phi times mmn is given by those two equations. From those equations, we know phi times Rn is equal to Ru. We can solve for TF, both for low resistance factor design, which is this right here, and for allowable stress design, which is basically omega times 2 Ru times n squared divided by A1 times FOY. Let's plug in and see what we're going to get. So TF minimum, it comes out to be square root of 2 times, that was 90, and times n squared, n was 2.78 squared, and divide that by phi is a 0.9. A1 came out to be it's on from the other one. A1 was 75, if you remember, and then time FY is 50. And that's equal 0.642 inch. Let's go to this one. TF minimum required we have is omega is 1.67 times 2 times 60 times 2.78 squared divided by 75 times 50. 0.643. Our flange thickness is 0.57. So the required is this. 0.642 is bigger than 0.57. So what we need, what we have, is not going to work. So this is no good. Same thing here. What we need is a thickness of 0.643, which is bigger than what we have is a 0.57. So that's no good. We need base plate. It's easier this way than to go ahead and get a bigger beam. So let me erase this, and then we go ahead and design the base plate. So when all these equations, we check, see if we need a base plate. Yes, we do. Let's design the base plate. Let's go to the AISC's equation J81. Take a look at that manual. We're going to go to this section J81. It's like concrete column base plate. Phi is 0.65, omega is 2.31, and the required area is basically your force divided by 0.85 F prime C. So it's equal here 90 divided by 0.65 times 0.85 times 3 KSI, and that's 54.3 inch square. Same thing on this side. We have RA is equal 60 times 2.31 divided by 0.85 times 3, and that's 54.4 inch square. So our B is equal, B comes out to A1, which we already have, divided by LB, and A1 is a 54.3, and our thing was 10 inches available. So that's become 5.43 inches. Same thing here, B is going to be A divided by L, and A is 54.4 divided by 10 is equal 5.44 inch. Here's your B. The plate is not that expensive, and this is a 7.5 inches right here. We know that that's a 7.5 inches. Okay, let's put the plate bigger than that. I go 8 to 10 inches. I go full burn if you want. You can go 9 inch, you can go 10 inch. But let's say use 8 inches. Use 8 inch for both of them. I mean, both design really use 8 inches. You'll be covered there. Now, coming back, let's calculate our N. So if we use 8 inches, our N is equal B divided by 2 minus K design. So N comes out to be, B is 8 inches divided by 2 minus 0.972, 3.03 inches. Same thing here. N is going to be equal 3.03, same thing. So let's go for both of them. Have that. We're going to go ahead and calculate the thickness. So T, the equation for allowable stress design, allowable stress design and load resistance factor design, they're pretty similar. One has a phi factor, and the other one has an omega. And let's plug in, so we're going to find T of the flange minimum is equal square root of 2 times 90 times N came out to be, right there, 3.03 square divided by phi is 0.950, B was 8, and LB is 10. It's equal 0.678 inch. That should come out similar. Is equal 2 times 60 times 303 squared, and then time omega 1.67 divided by 50 times 8 times 10. Get the same exact answer. Okay. So now we can say use plate make that 0.75 or 3/4 inch or 1 inch. I like 1 inch, but 3/4 inch, or let's say, or 1 inch by 10 by 8 by 10 by 8. I like this one better, but anyway, as long as you're not going to have any issue with the elevation, you can, I mean, you can do this ahead of time anyway. So they're both good. I hope this was useful, and if you like it, give it a thumbs up. Thank you. Have a great day.